and regression. But more importantly, our attention was on panel data and why, and the estimation approaches that to analyze. Like I mentioned last week, this is a panel data econometrics, so models are not particularly for. So it is you who assembles your variables based on your research question or question. You come up with a panel and then you analyze using these approaches or estimations. So this morning we are just going to walk through practically on using some software and some data set that is in a panel data form to understand what it is and try to reflect on those theoretical things that we mentioned last week. So get your eyes ready and on your machine or your device. We'll go through this step by step where we can go. Now, I think Dr. Kuch, I'm going to start by, okay, I'll share this. I don't know if we can see my screen.
Yes, yes, we can see the screen.
So this is a panel that I downloaded from two gentlemen who have used this on is Baltaji and Acom in their 2008 paper. They were very generous to openly share their data, which I used this because it is close to the examples that we used on wages of workers so that we can continue our discussion on that. So we defined the panel data as a data set defined by in two dimensions, or individuals or observations, but also a time dimension. So to Excel, which we are all familiar with. So I'll start with column A, and we are seeing the heading is ID, so individuals from number 1 up to number last. And we said, you observe for panel data video repetitively over time, depending on what you're asking or finding out. The second column is the time dimension. For their data set, it was a week, because we are looking at how workers' wages or earnings were per week for the week which they worked. And the L wage is a log of wage. We should have had wages themselves in levels of figures, and but he could only allow it down. XP is one variable they used as experience of that person, being a determinant of how much they would earn per week. Your experience measured by number of years that you've worked. WKS, from that data weeks that person or individual has worked. And then they had a dummy variable, which is gender. And one was for if the individual was a female, and a 0 if the individual was a male. Yes, we understand what a dummy variable is. It's a binary definition of whatever variable, usually yes or no, or a 1 or 0, depending on what it is. They also had education among one of the variables, which was number of years of schooling for that individual. And they another variable called occupation, and occupation, we're defining it as if the individual is in what they call a blue collar job. And then therefore you score a 1, it's also a dummy variable. You score a 1 if you are employed or working in a blue collar job, and 0 otherwise. Experience, this is experience squared. They had justification is why would you square an independent variable in your estimation? We will talk about this, but they included this because of for their estimation, which I also thought we could learn 1 or 2 things about it. So those are the variables we are going to be using this morning. So defining our panel, in other words, is here is individual number 1. And individual number 1 observed between time periods. This is week 1, 2, 3, 4, 7. So this is a sub panel. Then there is individual number 2, also observed over the same kind of weeks. And then we also have individual number 3, also observed over the same period or number of weeks. This is week 1, week 2, week 3, up to week 7. So these are sub-panels. When you bring them together, that's where the name comes from for all your variables that you are seeing. So if I delete this space, then it tells me how many. It's just now the panel data set that you have, meaning you can assemble this yourself. You don't have to. Panel data doesn't exist, always exist there for you to just download and go. You can assemble these yourself with your variables, depending on where you are collecting and what your search question is. I'll just control end to see my last in the video is number 595. So this is the last in the video for this from number 1 past individual number 1 up to individual number 595, which they used, also observed over the same period of time. When you observe these individuals over the time for the same time space, then put them together. That's what we define as our panel data that we referred to. So we are going to use this for our reference and demonstration. This is just a spreadsheet. You could also have this in SPSS or any other spreadsheet where you can always analyze thing that. So I'll close this and then we can go to the statistical analysis software package to try to demonstrate that we mentioned or used. Okay, now I understand. I mean, most of us on this call we are exposed to different statistical analysis packages where we analyze our data from once we collect. No one is a master of everything, but usually convenience is what defines. So most people here, I'm informed, use SPS statistical package for social sciences. Some people use Stata, some people use SAS, some people use R. As in capital letter R is also another you can use to do analysis. Some people use what? Python, some people use MATLAB. Now the new one, which is free, is also called Grentel. So you can, depends on what is really friendly to you. Now, I am going to be a little bit biased because I acknowledge that I have interfaced with SPSS, but I don't use it very often, so I'm going to try to drive you into Stata as a statistical package for analysis, which I'm a little more familiar with compared to SPSS. So the most important thing is we don't present these statistical packages in as and reports. Our attention is going to put and what we do or what you do with that output after you have analyzed. And I think that's the most critical issue here. Okay, so I'm just going to share Dr. Kuchi, just give me a heads up if you can see my screen and
Yes, you can see the screen.
all right. For those who are using Stata, please bear with us as we bore you this morning, but also as we revise together. For those who have never seen this screen or whatever, it's nothing magical, just like any other package that you are used to. In appearance and menu-wise, it is very close to SPSS. So this is the famous data. If you have never seen its interface or face, this is what it is. And I'll just take a few minutes to walk used to do briefly on the interface and what happens here. Now, this black screen or window is where results pop up. You execute execute a command or a request, and then your results come here. It is from this window that you can carry or copy and take to your Word or any other document processing place that you use for your write-ups and whatever. So there are 4 windows. I have this, which I've talked about, this black screen, which is the display or the output window. Everything you do will be coming here. If you want it, then you can take it wherever you want to take after you have done that. Now, there is a window down here where I'm seeing command. The command is, Stata has 2 options. If you don't want to go through the menu to find whatever you want to find, you can issue commands down here, statements, and it does what you actually do. We are looking from the menu up here, and most people who use Stata actually are more friendlier in using this command window than going menu here. The window which you are seeing as variables on the left of command, once you load your data, your variables will be displayed here. You can see them here. You can see which variable is which, depending on what you posted here. Now, the final window you'll see up here is a review window, meaning every execution you make, if you correlation and it brings results here, there is a copy of that command or instruction which is deposited here, which you can even save and replay later even when you close. So this is where commands are deposited or instructions are posted, and that's briefly the face of Stata for those who have not seen this before. But importantly, it has a menu like most of these softwares do. File is like what you do in Word or Microsoft Word, but of course with different settings that will come with here. Edit is the same function like on every face of your computer program that you use. Most commands under edit do the same thing. You can even see copy here, select all. So data, this is where you are, when your data is loaded, you can come and describe it, you can come and inspect it, you can create new variables, meaning manipulate them, you can come and sort, you can come and perform all those uh, manipulations with your data before you even start using it. So this is what data issues are. All your graphics, if you want to play your variables and a scatter diagram, a bar chart, or histogram, you come through this menu, and then it will take you to whatever you want to do. The statistics, this is the most loaded section on startup because this is the gist of everything, where analysis, the summary statistics, the linear models which you have specified and want to run, the count, all these estimation models or techniques, including even structural equation modeling. So you also do it in Stata for those who are familiar with SEM. So again, what takes you to whatever estimation technique here, like we mentioned before, is independent variable or your outcome variable. Is the one which tells you, oh, I want to do this, or it is categorical, or it is binary, will have logistic or probability of these issues menu that you can come. And then the rest are really help issues and window command. These are the things I was talking about, the results window, the review command, the variables, and the command windows down here. And that's it. All right. I think now we can kick off with the job for the day. Now, the first issue is data. You can also enter data in Stata, yes. Or maybe I didn't talk about these icons down here. This is open, this is save, this is print your results. This is, we'll see a log, I'll talk about this later. There is a data editor here, meaning if you click here, you can come here and start entering your data and variables, and then you save out. If you come here, this is browse. With browse, the same as editor, but in browse, you are not allowed to adjust or change anything. So it won't let you change anything. So if anything, you have to go to editor. Variables manager, if you want to manage your variables, and that's it. So the first step, of course, is the statistical package is to load data with it. And the Stata is compatible with spreadsheets, particularly Excel. And the first step is to, of course, save your data somewhere, wherever you entered it from. Could be Excel, could be SPSS, but SPSS and Stata do not share free file transfers. So if you are in SPSS, you may have to take your data to Excel and then bring it here. But for those who have Stata 17 right now, I think it came out 2 months ago, there is now compatibility. You can move your data from SPSS to actually Stata. I am running 15, so I don't have that we can talk about. Okay. So that is said, I'll come here, and the first thing is to data from where I am, which means you have saved your data somewhere. I'll go to file. We use what we call you import. It's just like whatever it is, importing it into your country. Now, Stata reads or accepts files which have extension CSV. So when you are saving your Excel file wherever it is, you must go in the menu down and choose this extension. Don't choose this because Stata might not read it. So it's delimited. I've demonstrated that, but now you just go and browse, find where your data is. I've already put here where I've been checking it, selected. So this If you say all file is not mentioned, that's what it is. And then the next step is to open. So it will ask you to just confirm and answer some of these things, but they are not a requirement. To just be sure that what you're bringing is what you intend to bring. So it tries to show you here your file which you are bringing. Is it exactly what you want? If you are okay with it, then you move forward. So here it is. It's telling me I have 9 observations and 9 variables, and about these observations, number of observations. So you see this window of variables has now come up, and my variables are now listed here. I can browse or edit. If I can say edit to just check if my variables have come, and this is and I'm comfortable with them. But if I wanted to change anything here, then I just click anywhere I want to change and then delete and enter that figure or adjust. That is only in edit data editor. But if you're comfortable, you have done everything that you brought in here, then just keep browsing and just check. This won't change anything, even if you make an error, then you move on. Okay, now so my data is here, but again, from this appearance, I don't know what these variables mean. So it's just, of course, to know what you're working with. ID, what does ID stand for here for somebody who's looking at? See, like we did this command here, it came here, and the variables are posted here. So I'm just going to take about 3 minutes, as you also just watch, to try to add, like in SPSS, the meaning of what you are putting, these variables stand for. So this has nothing to do with analysis, also just data manipulation. I'm labeling a variable which we are seeing as ID, and I want it is standing for individual or a person that was observed in this sample. We just put them in full quotation marks, and that is it. And that's what I'm referring to. Once you label, then it defines the meaning of this variable, wherever it is coming from. So I'll do the same for the second one. I'll label variable which you are seeing as T, and this is, I'm just going to call it time, and so that it also has a meaning here. And then I also label a variable which you are seeing as L wage. I'm going to call it log of wages so that we can understand what we are working with. And then I also do the next variable, which is EXP, and EXP stands for years of full-time of full experience, and then you close. And then I also label the other, which label variable called WKS, which stands for weeks worked. And I'll also label the variable we are seeing female, which means gender, which is 1. That's the gender, which is going to be 1 if the is female. Should have done this in Excel before I brought, but also for learning purposes, it doesn't kill us. I also label a variable which we are seeing as a Duke, and the Duke stands for years of education. And then I have a variable called OCC, which stands for occupation. And this occupation, we are saying OCC is equal to 1 if individual is in blue collar occupation, and 0 otherwise, because it is a dummy variable. Oh, sorry. And then finally, have a variable called exp squared, which stands for, let me just call it square of experience. The same justification, people interact variables, some people square variables depending on what they are. So these, at least now you can know what you are working with and how it is measured, or at least by scale what they stand for. So once your variables are in and they're also labeled and you know what they are, the first step, but panel data, I want to take this chance to start from a point where most of us are also possibly familiar with. Now, if you don't, the 3 common data sets that we know, cross-sectional, time series, and then panel. For the default type of data in Stata is cross-sectional. So once you throw in any data set, before you tell Stata that I want to run time series open data, it takes that data set as a default cross-sectional data that you have fed in. So if you want to run time series, you have to alert it that I want to perform time series estimations. If you want panel data, then you have to alert Stata that run or make panel data estimations. So for now, because I've not issued that requirement or request, the way it is reading it is as if it is reading cross-sectional. I just wanted to take it as a step number 1. Maybe we start from there where a little familiar before we cross to the other to see a difference. So assuming for now, hold your breath and say, assuming this data now is panel data, you analyze wages for workers by these independent variables which we have defined here. So first step, of course, is to inspect the variables which you are working with. The people are normally calling, the descriptives. What are you working with in as far as these are concerned? So if is the description or what these variables are, and again, if you don't want to go to the menu, you type here a command, and that is it. I just type here describe. It is as good as looking for it up here. And I also say describe data, so you can find it here. So you click here, it is the same thing as typing the word here. So those are the options that you can. So when I say describe, I just know what I'm working with. I mean, you may have not entered this data yourself or you have done it yourself, but you still need to understand what this is. So we are talking of 4,165 observations in total. This is the file size, number of observation variables is counting from ID up to experience squared. To get your 9 variables as listed there, and then this is the variable name. This is, it tells you that it is a a string, whatever, or an integer or numerical. We can add a value label if you want, but the most important is the variable label which you should define. You can explain this up to here depending on what you are defining for this case. And so run through this and try to understand what you're working with, just like we do analysis everywhere. You don't just run into estimations. You first need to observe what you're having with. The next thing is usually to run, some summary statistics, summarize what these things are. I know you don't want to report an ideal time, but I'm just going to include them. Just keep clicking on them, and you start with the just display everything that you want to see, the summary statistics, in other words. And once you do this table, which you can able copy and take whatever you want and talk about it. But you know what now these things are. In analysis, I wouldn't put ID and T in the summary statistics because they really mean nothing. This one is just talking about, the first person up to the last person, the year up to, or the first time period up to the last time period, and don't think these means make any meaningful sense. So maybe first variable is wage, which is in log. You want the mean, you want the standard deviation, you know what it is. The maximum is 4, the 0.6, minimum is 4.6, maximum is 8.3, and the experience is number of year, the standard deviation is this, meaning the person in this sample had worked for 1 year, 1 week, while in this sample, the person with highest experience carried 51 weeks. What was experienced by definition? We're talking of full-time experience, years, sorry, those are years of experience. It is weeks worked, which we are counting. The person, the lowest is 5, and the maximum was 52 weeks with an average of 46. So we could see in this sample, on average, most people have worked for 46 weeks or above. Female, this is a dummy variable. Again, the mean and standard deviation don't make sense here, but of course we work with all these things, categorical variables. It is a 0 if you are male, and it is 1 if you are female. So of course you don't bring this in the summary statistics. Education was education stood for years of education. So in this sample, the lowest number of years of schooling individuals in this sample was 4, and maximum of 17 years, with an average for this sample of 12 years. Again, occupation was a dummy variable. So again, this mean and its deviation do not make sense, because we are saying you score a 1 if you are in a blue-collar job or occupation, and otherwise it is a 0. It's just a dummy variable, another categorical variable that we talk about now. Experience squared. Why would you square experience in this case? Or why would you square an independent variable in an estimation that you think? Just like people interact variables, you get, for instance, education, and interact it with the female. What are you looking for? So first, usually the biggest justification for such a definition is the theoretical foundation behind your argument. You believe that there is a relationship between my dependent variable, which is wage, and experience squared. Theoretically, what does this mean? Squaring an independent variable, you are proclaiming that there is a quadratic relationship, meaning the effect of experience first may be increase, reach a maximum, and then wages start falling over time. Or that curve, that quadratic relationship, you are presenting a claim, or there is a theoretical justification. The relationship between wages and experience is not only linear. It also involves going down or going up and reaching a maximum, after which more experience does not matter, does not increase wages. Actually, it even leads to a decrease. Then if you believe in that, then you continue. Then you have a justification for that, theoretically. So, and in that kind of analysis or assessment, just like interaction terms, also usually must have that justification. And the examples here really matter. I mean, for going through experience and wages or earnings. Yes, experience is very relevant in how much you pay because of how long you have worked or what you bring in that institution. But over time, what happens when you retire? You'll still have your experience, and the experience will continue increasing. But when you have retired, wages will start going down. And this was actually one of the justifications why experience is not only linear. For Uganda, even right now, or where the world is going, what the world is going through right now, this could also be a justification. For instance, people have lost jobs. People have been suspended or whatever. Doesn't mean with experience, which they are still carrying, but some people, the earnings have started going down because of such issues. So those are some of the justifications why people square independent variables, why they interact independent variables in an estimation to do that. So these summary statistics also give you a hint. It takes you descriptive statistics at giving you a chance to know. But why do we do this? I mean, they are useful for both parametric and non-parametric variables. Whether you are doing qualitative or quantitative research, you still need to describe the meaning behind your variables. Most importantly, descriptives also alert us to know, to find out whether our sample that we are using is normally distributed. You know, a condition for normal distribution, which you almost have to mention in your analysis. But it also helps you track things like outliers. For instance, if I know that the highest number of years of school for this sample was 17. But because maybe somebody, because of entering data or errors that we commit, you find somebody has entered 100 years of school. It is possible, but for this particular sample, you stand here and say, how come I have a maximum of 100, yet the maximum possible response I got was 17. So playing these things helps you find out some of these issues. The one thing I want to mention here is descriptive statistics. Don't transform your variables into logs or into anything, then perform descriptive statistics. No. If it is somebody's income, what they told you, you present the descriptive of that variable in its level form, in its raw form, like some people like calling it. So you don't, I mean, I'm playing log of wage here, yes, because I didn't have the option to the real wage. Should have been wage, not the log one, to make sense of what it is here. So for descriptive statistics, as a reminder, you are supposed to play variables in their raw form as they exist. Of course, there are so many other things. Now we can also check for instance, normality, which is a very big requirement, especially for section on your variables. I'll just say summarize, and I want that variable I want that variable, which you can choose any variable, plain variable, or do for all of them. Of course, you have to almost check off all of them depending. So I'm just going to randomly choose, for instance, experience here. Normality, usually we are reporting kurtosis and skewness for whatever it is. So if I just add an option and called detail, then it gives me beyond mean and variance and maximum and minimum, so that I know more about that variable. And you know, with the normality, this is what matters. Beyond the other things up, we are talking of variance, skewness, and kurtosis. And if I'm to summon your statistics back, your variable is no more based on those two scores, the last two, skewness and kurtosis, if you remember. Kurtosis, which measures the peakiness or flatness of the distribution of that series or that variable. And the standard value here is 3. And we will say your variable is mesochatic, or it has a normal distribution when the kurtosis value is 3. So our score here on experience is less than 3. And if it is less than 3, we are talking of kurtosis being flat curve. So it is not peaked, but flat curve, which means there are more lower values, there are more values below the sample average when it comes to experience. If it was above 3, then we would say, then it would be peaked, and therefore we have more positive values above the sample average. For skewness, your variable is normal if the skewness score is 0 or close to 0. If it is positive, it means the distribution, skewness is a measure of degree of asymmetry around the mean. So that bell-shaped figure that people are playing. So if it is positive, we are talking of a long tail, a long right tail, which means for that particular variable, there are more higher values above the sample average, and the vice versa for negative skewness. So, and that's what you observe to tell. So for skewness here is 0.4. The normal distribution is 0, but you can always judge around this and say, well, 0.4 is not, may not be that terrible for me to look at. So those are some of the things. You can also do the same thing and maybe change the variable to another variable which you want to see. I'll check for weeks worked for this particular sample. So you go each and every variable. For skewness here, it is negative, which means it is a long left tail, which means for weeks worked, there are more negative values below, there are more lower values below the sample average for this particular data set that we have. For kurtosis, you can see it is way above 3. So you could say it is leptochatic, meaning it is very highly peaked. Therefore, you have more higher values above the sample average. And these are things we talk about preliminary inspection of variables, because you don't want to go ahead and analyze things which are not normal, then you'll be violating those estimation assumptions that you do. So you can go or you have to go each and every variable that matters to you. I don't think you don't need to do that for dummy variables, because those do not make sense for doing that kind of thing. Now we can also go ahead and of course, play around with some tabulations like people always want to see in terms of distribution. Again, you just come to, statistics. You can come to tables. You want frequency tables. You want other tables that could be here, some other statistics. You could do all these things depending on what to do. Let me just do one small thing people like always like to show for some of, I will tabulate the statistics, for instance, of wage, log of wage, but I want this by occupation. And whenever you put a comma, you are giving certain option that tell me about this particular thing specific to this. And I want you to display the sample and maybe the mean value. And so you can have this log or distribution for wages by occupation. Those in white collar jobs, you can tell the number out of the total sample, and those in non-white blue collar jobs are these and their respective mean. You can add any other variables that you can also mention. Of course, you can add other details which you want to also display, but for instance, if you want kurtosis, you just keep adding in this bracket. I could also ask for skewness according to this distribution. And once you do that, then it just tells you whatever. So for kurtosis, it is above 3, which means for log wage by, for those in non-blue collar jobs, it is skewed, it is peaked, high peaked, or it's a peaked curve because it's above 3. And when it comes to skewness, this is very close to normal for the group which is not in the blue collar occupation, while it is negative for, and then the overall issue that comes for that case. So for, there are those, some of them are visual, like scatter plots, which you can also use to check if my distribution is normal, but I'm just for demonstration, you can do that. And for illustration, of course, the other issue that we do is statistics, which are still also part of describing what our data set is. You see people running correlations and covariances before, pairwise correlations or partial correlations, depending on what you want to run. You can come to the menu and get them before you go maybe and regress, whatever you want to do. So I want, for instance, correlation is also warning you about some things before you go ahead, and I want to just do a pairwise correlation between these variables. For instance, I just want to see wage, which is the dependent variable. I want experience, weeks worked, maybe education, and the experience squared. Just add an option significance, SIG for significance, because I want to see if the relationships are significant or not. Again, like I mentioned, you can just copy this table and take it to Word and edit and make it look nicer according to what you do. So here, correlation, the attention will be on the column 1 because that's where I have wage and then it's independent variables. I have 0.2 significant at 1%. I have 0.05 significant at 2, and then there is some significance and positive relationships. When I come to this other one, this is experience squared and experience. No wonder the correlation is very high because there is a relationship between experience and experience squared. That's why possibly its correlation is way closer to 1 or very high, but that one you can justify. And the most important, of course, we rotate to this, or if you see very high correlations like this, then you start cautioning yourself, especially if they are not related like here where we know this was a square of this. If you see these high correlations, then start thinking of collinearity or these two variables looking the same or playing the same job in your estimation. And you consider dropping one, maybe for the other given what we can do. So correlation, this is of course Pearson, and the interpretation remains as before. The relationship between the two, it shows us a potential relationship between these two variables, or whatever pair that we are looking at for things that we do for that case. So that is, and maybe finally, then if it is after you've done that and you're confirmed with this, then you can go ahead and perform regression. You can of course come to do statistics, linear model, regression. There are diagnostics here after you have done that, but come to linear regression, so which is the same as I coming here. And then with regression, the first variable you place must be your outcome or dependent variable, which is log of wage. Then you can list all the independent variables that matter more for your estimation that you have specified. Of course, we get this from our data and the conceptual frameworks which bring you up to this level. So I'll put experience, I'll put weeks worked, I'll put female, I'll put education, I'll put occupation. I'll also see if experience squared matters. And then once you enter, this is the whole, this output. Even SPSS also brings this output for you. So most important here is not the starter which is giving us all the SPSS, but what do we do with these things? I know most of us understand what these things are, but just for revision and maybe revising and reminding ourselves as we continue working through this. Where do I start from? I'll start from the right-hand side here. Number of observations. This is your sample size that you have cleaned out and you are using it for estimation. And then you have the next is the F statistic, which shows how jointly significant your independent variables are in predicting the dependent variable. So this is the whole model that you have specified. This is your conceptual framework in simple terms. This is your econometric model, that your equation that you have written somewhere. So jointly, all these independent variables, they are talking of how significant this F statistic, how significant these independent variables predict your independent variable, which is wages. The P value for that we are seeing, the probability value for F, is the significance of the F value, meaning the smaller it is, or if it is 0.5 for 95%, with 0.05, then you are talking of your model being significant. People summarize this as goodness of fit, that what you conceptualized is significant, that what you wrote in that equation is significant, and therefore you can go ahead and rely on to make inferences for the population. Whether it is right or not for the conceptualization, it does not matter here, but the issue here is that what you specified is significant, meaning that you can go ahead and use it, that sample analysis, to infer, make inferences for the population. Now, R squared, as we understand, is the total variation in your dependent variable, which is wages or log of wages, explained by the independent variables jointly, not one at a time. Jointly, they took account for about 37 point or 38% variation in the log of wages for this particular sample estimation that we are using here. Now, what's the difference between R and adjusted R? This adjusted R is actually the R squared up here. For this sample is looking the same, but the adjusted R here is that R squared which you get every time you add extra independent variables in your estimation. Simply put, it is the penalty you receive every time you increase independent variables in your model, meaning that actually adjusted R squared can even grow and become negative if you keep on adding independent variables to the model, and that is why they're calling it the penalty of increasing. The penalty here is because you are increasing the probability of, uh, measurement biases, etc. So the model keeps punishing you because every time you put in a variable, you are distorting it. So while it is good for R squared itself, but it is not good for adjusted R. Some models even reach a point and say it is beyond, because like I've mentioned, this only keeps going down as more and more independent variables are put in the in your estimation. Of course, the punishment here comes because you may have collinearity issues, you may have inflating estimates issues. So that's why it is called the adjusted R for that particular cause. Root MSE, this is the standard error for the whole model which you have estimated. And we know what standard error is. It is, whatever you're specifying or estimating, it is how much deviation has occurred in your prediction from that coefficient or from that estimate. If there are any question, you can ask after that where I have not been clear. I will now cross to this, which we call or know as analysis of variance. Even SPSS also brings for you this issue. Now, to take you a little step back, when you specify your regression equation or that estimation equation like you have done here, the estimation here is based on assumption that you have explanatory variables based on your conceptual framework plus an error term. An error term, those are the independent variables which you could not add in your estimation based on either theoretical or data issues or of whatever other reason, but you know they exist and have influence on that. So because of that kind of regression, the notion behind the regression is to try to minimize the sum square of the standard of the residuals or the error term. When you say residual, means it stands for the error term component. To minimize the error term so that they are close to zero so that what you specify becomes a true prediction of what you are actually conceptualizing. So that's what you mean by regression. That's when you're regression, that's what is happening behind there. So there are sum of squares divided into two. One for the model, meaning for the explanatory variables which you have used here, and then the other one for the residual or for the error term component, which you have also explained. So meaning this plus this should give you the total. That's why 335 point something, 55.1 should give you the total sum of squares. Again, the issue behind the regression is minimizing sum of squares, and that's why they call them, that's what we mean by regressing. DF is degrees of freedom. Degrees of freedom refers to the number of restrictions you are making in your estimation or conceptual framework. It is the total number of independent variables, including the constant, but defined as K minus 1. So K is the total number of restrictions, which is all your independent variables, including the constant, minus 1 for the model. I'm talking about now 6 here. So K minus 1 is the degrees of freedom for the model or the explanatory variable that you have put in your model. So K minus 1, the total number of restrictions is K, which I'm saying those all your independent variables plus the constant. Here I have 1, 2, 3, 4, 5, 6 plus a constant, it makes them 7. So K minus 1, K is 7, minus 1 as a rule for degrees of freedom, right? That's where we are getting this 6. So for the residual, it is N minus K, which means a total sample size almost minus total sample size minus K, the total number of restrictions, which is 4, total number of sample observation is 4165 minus K, which is 7. And that's what we have as 4158. For the total, it is K, you just sum this and this, which should give you these degrees of freedom for whatever we always refer to. The mean square is just the averages of this sum of squares, which is arrived at by dividing the total sum of squares with the respective degree of freedom. Meaning 335.13 divided by 6 should give you this. Then 551 divided by this should give you this. And then this divided by this should give you that. And that's where we come from. And then finally, for our model that we always come to talk about and interpret, these are the coefficients. I'll start with the coefficients here. And you know what, these are the estimates. These are the betas that we are looking for, the impact of the independent variable on your dependent variable. Here we have log of wage. Here we have experience, which was number of years of full-time. Means an additional year of experience is associated with 0.04, which is about 4% law of increase, an increase because it is positive in wages for those workers. I am using a percentage here because the dependent variable is in logs, while the independent variable is in levels. So when you increase here by 1 unit, the dependent variable has to increase by this percentage. It is 9% form. If wage was not having a log, then the 0.04 would be dollars or shillings or whatever wage that person is paid for. But an increase in experience arrives associated with 0.04, for instance, shillings, if that person was being paid in shillings for that particular case. If we had log of wages and also had log of experience, then we would say everything would be percentage, meaning a 1% increase in experience would bring this percentage increase in wages. And that's what we always do and explain or represent in all these cases. The standard error, like I mentioned before, in regulation, this experience here, your computer, your SPSS or Stata, has so many coefficients of experience, but it goes and chooses the one which is more efficient. Which is more efficient means carries the lowest or minimum standard error of variance. So this standard error, which we always see this, represents how much deviation has occurred from predicting this coefficient. That's why it brings a standard error for every coefficient. And that's why if there are so many coefficients of experience, but only the efficient one is picked up. So we are looking at the smallest coefficient possible for this particular case. The t-value measures the number of standard errors the coefficient is from 0. Number of these standard errors where this coefficient is from 0, because the hypothesis here is for any coefficient, the hypothesis here is you want to test if each of these is 0 or different from 0. That's what coefficients and hypothesis testing here are. So you are testing if experience matters or it does not matter. You are testing if experience predicts wage or does not predict wage. So we are looking at number of deviations deviations that has occurred from predicting this coefficient. And we can compute it as meaning the standard coefficient, the coefficient divided by the standard error gives us a t, the t value. So 0.41 divided by 0.0022 something should give us this value. And that's why we say a value for the 5% confidence interval, because the critical value for at 5% is 1.96. So any value above 0.196, although people summarize it to every value above 2, using a t statistic, it means it is significant, but it is 1.96. So we have 18 for experience, which means even if I don't look at the p-value, I can use this and conclude based on this sample. And that's that experience is significant. But more importantly, what is the p-value itself, which we are always looking at critical case? The p-value for whatever is defined here is the smallest evidence available, or the smallest evidence that is required for you to reject the null hypothesis. That's the p-value has so many meanings, but I think that's the simplest that we can go with. The smallest evidence available for you to reject the null hypothesis. Remember, for us in the social sciences, of course, including economics, we don't have accept and reject. We either reject or we fail to reject, depending on what your hypothesis is. We can't say we accept this because from theory building and the errors and all these issues and the subjectivity cannot allow us to say we are not like in natural sciences where they have to be all sure. And so for us, the language is you either reject your null hypothesis or you fail to reject it. So the p-value, you are looking for any small evidence so that you are in a position to reject your null hypothesis. No matter which way you have stated it for that particular course. And that's what it entails or stands for here for every factor. And then finally, the confidence interval. This is the level of confidence, if I'm to use the same word for the lack of better word. Most importantly is if your independent variable is significant, then its coefficient should lie between these lower and upper confidence levels. So which means if it is significant, the value is between these two range values. This is the lower and this is the upper one. If the value is not significant, the variable is not significant, then it will be outside this confidence interval. That's what can summarize for this particular case. So you can go ahead. This is a negative. Now, what would you mention here on female, for instance? We have a minus 0.44 for a female. It is a dummy variable. What does this mean in relation to wages? A dummy variable usually has a base category, meaning you don't interpret it alone on its own. It is relative to the other group. So the language here is for relative to males, which is the other category, females are associated with a decrease in wages for this particular sample size. Decrease because of minus, and it is a percentage because the dependent variable is in logs. If it was just if it had no log, then we would say compared to males, females are associated with a decrease in wages by this particular amount. And I would prefer for say that's how I would interpret the 0.44. For occupation, you're also seeing a negative. It is also a dummy variable and it is significant. and which means that relative to those who are in non-blue collar occupations, individuals employed in blue collar associations occupations are associated with a decrease in wages by 0.12%. I'm using a percent here again because the dependent variable is in log. So you have to always be careful when we are talking about these issues. If all these were in logs, then it will be percentage as move to those particular one. Then this is a constant. I think I've demonstrated using these for experience. You can still relate for the others if there is any question. Dr. Kochi, I think I am pausing there for 2 minutes if there are any questions now so that I can officially cross now to panel data for the day, but I just wanted us to start from that position for review first.
Thank you so much, Bernard. I know the first bit of the presentation could have raised some of that maybe it could take some few couple of questions, maybe 2 or 3, yes. And then we can move to the next. Yeah.
Okay.
Okay. Any comment? If there is any comment, I see some on the chat room responses have been made. But okay. Yes, Sylvia. Sylvia, you can go ahead and unmute your mic.
Network.
Thank you very much, Dr. Kochi, and good morning. Hello, good morning.
Yes.
Hello, good morning, Ben.
Morning.
Okay, thank you. Thank you very much, Dr. Kochi and Mr. Presenter. I just have 2 simple or basic questions. One is that what's the difference between the pairwise and the Pearson correlation matrix? Because some people use Pearson, others use pairwise. And also in economics, we seem to use this correlation as a diagnostic test to see if our variables are not, there is no correlation. But also they are used for testing relationships and to actually go ahead and discuss. So I'm just wondering, at what point do we use it as a diagnostic? At what point do we use it for relationship kind of testing or running relationships? And the other question I also wanted to ask.
Yes.
It's like we're losing a bit.
Yeah.
Is that
Sylvia.
Is it
Sylvia, we missed you a bit. You come back again.
Relevant. What producer R squared? If you're not hearing me now.
No, you come back again, please. Just on the last.
Yeah, the last question. I was asking that is it relevant to also produce the R squared for choice model or in a choice model, for example, a logit model? And if yes, what is the advisable minimum and the maximum value for R squared? I hope you've understood.
I've understood, Sylvia. Thank you for your question. Is pairwise Pearson, the bottom line is correlation. It is the difference, it is just in terms of presentation, but all of them are just talking the same thing. I don't think you'll be crucified for just saying correlation and then another person is saying pairwise. But the pairwise, because you are particular between the two variables. You are trying to be specific with this particular detail which we did. Same. The question which followed that, sorry, I skipped that one. Let me go to the other one for choice model. I want to just see if I can, okay. Choice models first, Sylvia, is when your dependent variable is a binary outcome or a choice outcome. For instance, to go or not to go. It is not a figure like 10, 2,000, like 10 million. No, it is a choice. It is a decision between or among options that you have. For instance, to adopt or not to adopt, to use or not to use, to increase or not. Those are that's the fundamental decision behind a choice model. Like I mentioned before, all these estimations, it is your dependent variable or outcome variable which directs you or guides you which estimation you should run. Now, choice models, because we are talking of, for instance, a yes or no, you are talking of to adopt or not to adopt this approach, to increase, to eat or not to eat, it is a choice variable. So it is an estimation of the likelihood, or it is let me restate this. Choice models predict the probability of an outcome happening, of you adopting, for instance, energy saver or not. What is the probability that Sylvia is likely to buy an energy saver? So your dependent variable is a choice option with so many independent variables which you can list. Now, the independent variables don't have to be also choice or dummy variables. It can be a mix of all types of variables, but the dependent variable is a choice outcome. There are also such cases where the dependent variable or the option is you have more than one. For instance, in transport, do you want to use a bus? Do you want to use a private car? Do you want to use a train? Do you want to use a bicycle? Now, it is not only two choices. If you have more than two choices, then this is what you are going to see as multinomial, probit, or logistic. Multi because your outcome variable is a choice variable, but it has more than two choices or variables. Again, there are conditions that define this for that. When you estimate a choice model, it gives you what you call a pseudo or the would-be R squared, but it is not an R squared. Because you are talking of probability of something happening, we cannot stand on our feet and interpret it as the variation in independent variables because of that, because of in the dependent variable, because of the independent variables. It is a possibility. There are probabilities of something happening or not. So we are not sure. That's why they call it the pseudo R squared. But it only gives you a hint. Of course, you can't interpret it the way you interpret the ordinary R squared here. It only gives you a hint of what variation you are having because of what you have specified. Maybe we'll do that, Sylvia, for choice models outside this for more illustration.
Okay, thank you. I think Dr. Joel.
Hello.
Yes, please.
Yes, Dr.
Hello. Yes, Ben. Thank you for the eloquent presentation. I wanted to throw more light also on the confidence intervals. If you have noticed that for those limits, we don't have zero in between. So in terms of significance, that can also be another basis of also checking whether those values are significant. In addition, I'm happy that you have brought that aspect of interpretation where we talk about the unit changes and percentage changes by introducing,
Dr.
especially
Gideon.
when your interest is to eliminate is.
Dr. Gideon, your network is
Hello?
breaking. Your network is breaking, and I wanted you to repeat what you just said. Your network. Hello, yes, now clear. Your network was breaking, but you can repeat what you just said, please.
Oh, thank you, Dr. Michael. I was saying that I'm happy that
There's still a problem.
Ben has tried to highlight one of the challenges we usually have whenever the first we to talk about the unit. I think we want to talk about percentage changes.
Maybe doctor can type
especially when that come to interpretation. Find that those common issues. So that explanation of elasticities. My challenge.
No, maybe you just post it. It looks like the network is having problems.
Right.
We're not getting you at some point. Okay. Bernard.
Yes.
Bernard, I don't know how we could proceed. I see the first section of the presentation has really raised a lot of
questions.
So, and I don't know how we could be able to proceed. Don't you think that we capture most of these issues first? Because we might, I don't know. What do you think?
I don't know if I want to unshare, but I lose but members might lose the screen. I don't know to access the issues.
I don't know what would be the best mode. I think maybe because I see
I think here we are really understanding these things as much as we can, so we could assess those before we see. If we can't finish panel today, we can continue another time.
Okay. So maybe respond a few questions.
Okay.
Then you introduce the other bit, and then we can see if maybe we can again come back next week, next weekend.
Okay.
Yeah. Okay. So you pick a few which are critical, and then you can proceed. Then we can be able to have again first address these very comments, and then we come back. Okay,
Right.
Dr. Gideon, we lost you a bit. Maybe you just type the response.
Yes.
And then I would like Bernard to continue. Bernard, please.
And somebody called business synergies. What is the information value of a dummy variable statistic? Why are years of education not squared like experience? Now, let me start with the second one. Years of experience are not squared. Again, I just brought this for demonstration purposes. You will square years or you'll square any other variable, it has to come from some theoretical justification. For years, as time goes, there is possibly no quadratic relationship between years and earnings, because as you earn, you continue working, incomes are most likely to stay the same or increase until your retirement time. After retirement, then you will be officially out of work, and I don't think we'll bring that now as a determinant as far as wages are concerned, because you are officially out of work. But you are talking about this sample where somebody is working, and there is a possibility that he may may bring out to that. But most importantly, the bottom line here is, please, usually there is some theoretical justification behind, just like moderation or interaction. You don't just, mix things because they are looking nice. Somebody is asking, kindly explain again F values and the probability value. Also put more light on R squared and adjusted R. The probability value, the F, which had in bracket something, where I started from, that F value is your overall fit of the model that you have estimated. Again, it explains how jointly significant your independent variables are in predicting the dependent variable. All the variables you have specified as independent variables jointly, how significant are they in predicting your dependent variable? That's what the F value is. And its corresponding probability value is just telling you at the level of significance at 0.05 or 0.01. So if it is 0.000, then that is of course 1% catered for. So we would say that model you have specified is significant. It does not make it right, but rather right or wrong, but it is only on the significance of what you have specified. You could loosely say that my conceptualization, my conceptual model is significant because that is where you are picking your dependent variable and all your independent variables for that estimation. The R squared alone, R squared is the total variation in your dependent variable explained by the independent variables. So as very plain as that, the percentage of variation of your dependent variable because of variation in your independent variables, again jointly because you are talking about the overall model. The adjusted R squared is, like I mentioned, it is a value which you get every time you include an extra independent variable in your model. It is the penalty you pay for increasing independent variables in your estimation, which means it keeps going down because you specify the first model you run. You bring other variables, you keep adding. The overall value of R squared will go up, but the adjusted goes down because of the possibility of running beyond the limits for the other problems that the independent variables might bring, including inconsistency and efficiency, making estimates inefficient for that particular cause. Jonathan, what determines when to use linear logit to beat regressions? Please, this is the characteristic of your independent variable. I think I've moved through this. Linear, the most common pronounced approach to regression analysis is the presumption, the 6 characteristics or assumptions that we have. One, that your population estimation or conceptual framework is linear in parameters. Number 2, that the data generating process is random. Number 3, that there is no relationship between error terms and the independent variables, but usually it is a mixture of all variables. Discrete, your dependent variable might be discrete, your dependent variable might be continuous, but some kind of value that you are learning on that, assuming that the relationship between what you are estimating is linear. A logit is a choice model approach or estimation, like I mentioned to Sylvia before. even a little bit, where the dependent variable is not a continuous, is not a number like 10 or 50 or whatever, but rather a choice. The dependent variable, mark my word, dependent variable is the one which determines this. It is a choice. You may say, you want to to analyze or understand why, if people are likely to adopt solar in Uganda. So the option is here is to adopt solar or not. Now, sometimes if it is binary, then you only run logit or probit and the 2-bit equations that you will see in your menu. But if the dependent variable is a choice variable and has more than 2 choices or options, that's where the word multinomial comes in. So you'll start with multinomial logit, multinomial probit, like that, for you to put this particular kind of truth. When do we use what model among the many listed in the statistical package? I think I've talked about that. Geoffrey is saying the nature of variables determines the regression model for logit. Yes, mainly. Okay, thank you, Geoffrey, for adding on that. Why years of education not squared? Yes, I just use this for illustration, but you may have a theoretical, you must have a theoretical justification for also squaring age. I mean, the debate here is say age does not matter as it keeps going for a person's lifetime. Incomes increase or remain constant, but may not likely reduce. And that's why it is not mentioned here. Kasim is saying including experience squared in our model doesn't it contravene assumption in reality? No. Kasim, linearity assumption is for the parameter or the estimate, not the variables. So variables can have x cubed, can have experience power 4. There's no violation of that particular case. It is only if you say beta squared behind the experience, that's when the linearity assumption collapses for that particular case. That would mean. As I see, I think somebody has a...
Okay, yeah, thank you so much, Bernard. I think I want to beg the participants that we allow him to continue a bit, then I will give him again time to explain most of the comments. But I know that given the fact that we are using starter, most of the people are used to SPS, so I think so. But all the same, we shall give you adequate time to deal with most of the issues. But I also note that there's a comment on the chat board. So Bernard, please, you continue. I will give all of you chances to raise more questions and also make more observations. I'm also sorry we missed the comment from Gideon, but I think let me allow you, Bernard, to continue, please.
Okay. I was trying to share the file so some people who have actually this can get can put it on their computer and run these things. Those who have SPSS or starter or whatever you use. Okay, I think the file is there for use. Okay, let me see what we can do for now. Like I started before, by default, if you bring any data set to Stata, it will take on or assume it is a cross-sectional. So whatever we have been doing here are explanations and analysis based on cross-sectional assumptions that we have been talking about. For time series, for Stata, you have to alert it first that you want to run time series characteristics or estimations. And therefore, for panel also, you have to alert it that you are going to now, I'm using these data sets to run a panel data for this particular assessment or estimation. I don't think we will finish this, but let's do the preliminary. Okay. First, I'll sort by ID. This is just really and time. So for panel data set is you are just now I want to just inform starter that please whatever I'm going to do going forward only panel data estimation. So it is XT. You say set. You have to start by ID, and which is the cross-sectional dimension, and then by time because it is N and T. So right now, and that's why we from this step forward, you can now start running your panel data estimations. And what we are seeing here is panel data ID strongly balanced. Remember, we talked about unbalanced and balanced panel, which means this data set that I'm having here, there are no data gaps. All the years for every individual are all having data or existing. That's why it is saying strongly balanced. The time variable varies from 1 to 7 if we can just play this so people can see. So meaning from individual 1 up to individual 595, all of them have complete data for the 7-year period that they were analyzed for this particular data set. Okay, and so the change, which is a delta, is 1 unit between the cross-sectional dimension is just 1 unit. I mean, 7 minus 2 minus 1 is 1. 3 minus 2 is 1, like that. That's what is referring to, even for these dimensions. So I start now the same issues we did with cross-sectional dimension. Again, I need to describe what I'm working with to understand what am I working is. So going forward, every command here or execution, you start with XT. By saying XT, it is now you are sending, you are using, it is recognizing panel data commands or instructions which you are doing. So when you just say describe, it won't be bring you panel data dimensions, it will bring the cross-sectional dimensions. So XT means now panel data, and if I say enter, it just tries to tell me again to understand what this data set is. For the cross-sectional dimension, which is ID, it is from individual 1 up to individual 595, like we saw. And then that's where the small n comes from, 595. For the time dimension, we have 7 periods or 7 weeks. And that's what it stands for. Again, changing between the periods is 1, spans for 7 periods. The distribution over time, 7, 7, 7, 7 is just for constant between minimum and maximum time periods. For cross-sectionals, just frequencies, we have 595 individuals, which is still the 100% that we had before. I can also now play the summary statistics. Even if I just stopped SU sum, it doesn't matter. You don't need to finish summarize or sum. I'll try to bring all variables even when ID is irrelevant to talk here, but I don't want people to say, why didn't you bring that? Let me just play everything so that we see what happens here. Now, this is one of the most unique tables or figures for summary statistics when you have panel data. So if you remember last Sunday, we talked about variation, and this is what makes panel data unique from the other cases. Even the summary statistics you don't bring. Again, I want to almost ignore the first 2 variables because it's just time and individuals. So you don't want to, this interpreting this is as good as, meaningless because it doesn't really attract anything. But Let me start with LOH, but even this, we have overall, we have between, and then within. The overall is for the whole sample, not controlling for time and not controlling for cross-sectional issues. For between, you are holding time constant and observing the cross-sectional units, which is individuals here. For within, you are observing a person or an individual over time. What do I mean here? For the overall cross-sectional issues that the overall is for the two dimensions combined. Now, when you hold T constant and you observe in person 1, person 2, person 3 in all that variation, that's what we are seeing as within. No, that is between individuals, between person 1 and person 2. When you observe person 1 over time, over the 7 periods, that's what we are referring to as within. And so we always report those two dimensions for most estimations when you're talking about panel data. So this for wage, what does this mean? The average, and like I mentioned, these ones don't make sense interpreting them because you're just listing people. But I want to come here. But between, if will ask why is this one 0? Between individuals, why is this? This is variation. The mean here is 6.67 for the overall. Now you don't need mean here and mean here because the overall is what determines the variation here. But what does variation? This is the standard deviation. Again, the measures the measure of dispersion, the deviation that occurs between a variable from its mean. Now, what you only need to understand here is for wages, there is a higher variation between individuals compared to within a person over time. This is individuals, between individual 1 and individual 2, this is the variation. This is the variation within the one person, but over the 7 periods that we are looking at. And that's the only thing, the most important interpretation here is the variation within and the variation between. There is higher variation between individuals for wages compared to, there is also variation over time, but there is a higher variation for the person over time between individuals compared to over time. The same thing here for experience. Experience varies. Hello? Experience varies more. There is higher variation between individuals in terms of experience compared to within, and there is almost no variation because within the person experience may very little variation over time for what you mentioned. And then weeks worked, variation is higher within this is over time compared to variation between individuals. Now this is what makes sense. That's why I played this to show that somebody asked about information on dummy variables. Now, between individuals, there is variation because you have male and female, yes. But within a person, I don't think your gender changes over time or is assumed to be constant, apart from, of course, it is not a perfect example, but over time, your gender is likely to be the same for that particular case. When we come to education, there is variation between people or individuals. But most likely, but within a person over the 7 time periods, we can't see any variation. Now, for individuals, this is also a funny statistic though. For individuals, for occupation, if one is for those in blue-collar jobs, so between individuals, yes, most likely variation is higher, but within the same person over time, I mean, if the race is because of other factors, so same thing here. So the total sample size, the 416, is n times t, which means 596 times 7, which gives us this particular case or scenario for interpretation. And that's what the summary statistic would appear for panel data. So again, what you choose to summarize should also be, you can't bring this and present in your write-up or your paper because this does not make sense. And even most of the dummy variables, again, summary statistics don't make sense. For instance, what is the mean of male and female when you are just saying 0 for male and 1 for male? This mean is useless. So we are always reporting those variables where variation is where variation makes sense for that particular case. So again, so which sends me now to the estimation methods that we discussed last Sunday. There are generally 4. There are other estimation approaches for panel data approaches, but there are generally 4. And the first case we looked at, if I'm to just put the heading here, was the pooled OLS estimator. Now, for the pooled OLS, if you recall, we stated the general panel data model, which comprised of the dependent variable, which was equal to the constant plus beta times the independent variables plus CI, which was the unobserved effects, and then plus UIT, which was the official error term. Now, for pooled OLS, if you remember, assumes that for me, those heterogeneity or observed effects do not exist. You just simply ignore and run your estimation as if they don't matter in this case. That's one way of managing the heterogeneity that we talked about. So it is actually as good as just the same regression that we did here. If they don't matter, then we just do, it is like an OLS, the official cross-section analysis, which we mentioned here, because for you, those CI, the heterogeneity does not matter in this particular case. And so this is where it comes from. That's why this is resembling the other estimation I ran, because it is the same on that assumption. We just ignore the unobserved effects and run an equation. Of course, you must have your own justification is why you think you are running a panel data for this particular kind of sample, but it does not arise for this particular, does not matter for this case. The second estimation was the one we called the first difference. And the first difference, if you recall, estimator, if you recall, was that you are taking changes for all the variables largely to correct for for one period changes for each individual to correct for potential omitted variable biases that may exist. So you just get the original, equation that we have had, and then you take the difference for the variables that for all the variables that have to be differenced, and then that is it. You lose out then the heterogeneity disappears, like we saw in the last illustration. So as simple as just running, again, it is reg. You can say d dot LOH, which means you are differencing your dependent variable, and d dot, the next independent variable is experience. Then d dot, the next independent variable is weeks. But I can do this in short form, just to difference everything. Instead, come here. This is what I'm going to estimate by entering this command. I'm putting that bracket and putting a d behind and a dot. It means difference every variable which is inside here. That's the shorter option to this, and then you run. You have your some good explanation is here and justification is here. Number one, note experience omitted because of collinearity. Female omitted because of collinearity, which I wanted intentionally to talk about, and then also education omitted because of collinearity. Now, first, how do you interpret this? Let me start with the interpretation before we go to the changes one. One period change in number of weeks worked is associated with because this is in percentage, yes, the wage, so it will be in percentage. Is associated with a reduction, percentage reduction in wages for workers by this value. That's what it would mean for. However, going by the t value and the p value, this coefficient is significant, so we shouldn't lose sleep over it, whatever value it is, because it does not matter for this particular case. The same explanation would happen here, but we will have to say, because it is a dummy variable relative to individuals in the non-blue collar occupation. Those individuals employed in a period change for individuals employed in blue collar jobs associated with 0.02 percentage reduction in wages for that particular case. Again, it is also not significant, so we don't bother talking about this. The only variable I see here which is significant, or we should cause for implication or make implication, is experience squared. Of course, squaring, you are claiming a quadratic relationship between here, meaning that experience can increase wages, reach a maximum, and then afterwards drop. So why would that happen? Why would that reduce wages? Maybe over time, changes in experience do not actually increase wage, but actually reduce wage because of that classification. Now, why was this and this omitted? I'll just go to the data itself. I'll start with female or with education. The same individual change changes. 9 minus 9 is 0 over 9 times gives you 0. Because education does not change for a person for this particular sample as it states or exists here. We see person 2, 11 years. If the first 3 years was 11, and then the next 4 years it was maybe 14 or 12, then would have that variation standing up. And therefore this would mean that would bring the variation. But here, why it was dropped, if you take changes, you'll have zeros all through for each individual, and that's why it was dropped. The other variable was also females, again, for this particular case, depending on what you are representing here, but because it looks familiar to this other dummy variable in terms of, for instance, for the first person, it is 0, 0, 0, 0, which means we don't, but even if it is male. And then for occupation, also have 0, 0, 0 for the first person. So for this analysis, it seems like this variable is the same as this because of their nature of construction, even when they mean different things. So a warning here is too many independent variables that are dummies are likely to make you run into collinearity issues. That's why it was possibly dropped. Which other variable? Experience. I don't know why today. Was it experience? I think it was experience, yes, for experience that was also dropped when you difference. It looks like if we went and observed the experience for all the individuals up to down, you would have somewhere who individual who had a constant score, and when a difference goes to 0, and then it would bring all. That's why it was potentially dropped, but at least for it, it had variability. So if you remember the assumption on collinearity, the assumption is none of your independent variables must be constant. Constant meaning having a value from 1, 2, 3 up to down. It is not varying, it is not changing from person 1 up to person last. Then you'll run into collinearity issues. Or if two independent variables mirror some linear relationship among them, between the two of them, then they'll drop one at the expense of the other. So that's assumption number 3, I think. What we talked about is what brings all these things. So sometimes the approaches to this, if this happens, consider running a model with only one, and then so that it is kept in, and then try and see, then bring the other. That's why people go for hierarchical, estimation is when you start presenting some of these things so that you see if there is. I'm very sure if we removed one of these dummy variables, then we wouldn't go through those issues. Dr. Kochi, in the interest of time, how do we proceed? I have 2 most important, which people really need to understand from the onset, and they're a bit extensive.
Okay, thank you, Bernard. Like I said, there are so many comments, and I see even what you have again presented actually is raising more very interesting, intricate information. I think, like we had earlier discussed, we can give you next week again when you proceed. And yeah, so members, can we raise comments and questions? And then, but first of all, before we go into that session, I want to acknowledge everyone for attending this morning session. More specifically, I want to appreciate our senior colleagues. I know some have got disrupted by the network. I want to acknowledge Professor Janet. I also want to acknowledge Dr. Evelyn Akesh, Dr. Tom Patrick Mugizi, Dr. Goreti Cheone, Dr. Joel Kabagambe, Dr. Ibrahim Senze, Dr. Isaac Kayongo, Dr. Gideon Kuzinza, Dr. Ahmad Walgembe, and Dr. Sada Chimuli. I think all of us can really bear witness that Bernard has done a great job. Bernard, thank you so much for sacrificing your time and enabling us to have insight on the aspect of data analysis and also looking at panel data. I think this is really a great continuation of the previous lecture, which was wonderful. And for me personally, I've never used Starter, but I think it's a friendly version. And so like I was saying that I think there are challenges also a bit on that, but I think you have really been a very good teacher that we learned a lot. So members, I want us to raise questions. I saw there was a lot of interest in asking questions, making comments from the first section of the presentation. And senior colleagues, you can be able to make more submissions, additions, students, everyone. You can raise up your comments. Again, once more, Bernard, we really appreciate you for the comments. And I see some questions already in the chat room. So maybe as we allow, because he has really been talking for a long time, and is there any senior colleague who would want to make some comment before eventually, as even other people are making questions?
I see one from Millie. At what point is the difference? I'm sure she's talking about the differencing. At what point is differencing required? Are we imposing a stationarity for the continuous variables? I'll start with your second issues. Yes, that is one of the requirements or the reasons or suggestions for actually going for differencing. The most important thing is, one, you are dealing with the heterogeneity or unobserved effects, but for a variable that may have different characteristics. Now, when you are differencing, you are taking periods over what you may have also that relationship, that quadratic relationship between the variables that you are doing. So differencing could solve that, but the fundamental and theoretical justification for differencing is the likelihood. Is the likelihood of omitted variable biases that may exist, that of course arises from your specification. But it is one way of managing the heterogeneity, the unobserved effects when you have a continuous variable. Of course, the dependent variable which is defining, which would wish to keep stationary. Stationarity is a time series dimension concept for members who are hearing this for another time, that you cannot run a regression when one of your variables is non-stationary. It is not stable. It has ups and downs. It does not settle along the long run mean. So that's what the stationarity is, but maybe that will be for another time. Because panel data has also time series dimension, and that's why Mira was mentioning of stationarity for potential stationarity for one of the variables. Okay.
Okay, thank you so much, Bernard, for the response. Again, I've seen a comment from Chisungo that he will need to read more, but very insightful.